So let's come to part 2. Now it's really non-commutative. I mean, it was non-commutative before too, but so what do we need? First, spaces. But there was enough discussion on spaces. So we think of Gelfand isomorphism, isomorphism between categories of local compact Hausdorff spaces and abelian C-star algebras. So I just say, well, in the quantized case, in non-commutative, deform it. And I will not say much about it except mumble a few examples and then give you one and we will work on it. I mean, that's not the main issues of it's not our input. What next? We need a differential calculus. You remember, I mean, the final goal is, of course, to establish a quantum field series. So what did we need? We have to have what are differentials, what are vector fields, differential calculus. But very nice, it exists on any associative algebra. So very good. It's beautiful. There are many. A universal one, trivial cohomology, and then projections to the special ones, and of course we have to have certain requirements, but I'm not going into such details these days. Now next we need fields. In the classical case, these are sections of bundles, and as we learned, these are elements of finitely generated projective modules. So you have heard about the projector today too. So it's really a stuff which is highly developed. Many of these are not so easy, by the way, these projectors sometimes. Next, we would like to have an action for the fields. So we have to integrate a top form. And here, of course, some traces, let's say, generalized trace and so on. But now comes the input from our physics requirements. More or less, well, we have to watch. We might regularize. We have to establish a quantum field theory. That means we have to integrate of all fields. Wiener measure, for instance, or two-dimensional Klim-Jeffrey measure and all these things. So we have to establish it in our case. For sure, we have to put some cutoffs. I mean, it would be much too much to say, it should be finite anyway. That's what loop quantum gravity people like, but from the beginning, but okay, I don't say anything more. We will regularize, and then we have to remove the regularization in a clever way and renormalize, of course, on this way. Well, and that's, of course, a big challenge. Now, what about spaces? Well, you know everything. I mean, we learned also in the early days about this zeta deformed torus. So the algebra I write now, of course, like this, and we know what it is. And we know derivations. You saw it today, and so on and so forth. So non-commutative torus is well established. It took years that people managed to handle it on this level, more or less. And the first were Reimer Wulkenhaar and Thomas Kraszewski. Sorry? At one loop, but it was the first time that the input, yes, at one loop. Therefore, I said more or less. I'm sorry. It was 99, something like this, yeah. But that was really a new transition. Of course, on this manifold, so to say, it's, to my opinion, a challenge to go ahead. I mean, because of small denominators, resonances, and so on, like the KAM theorem, KAM theorem, you have to enter into troubles, enormous many troubles. But they managed, I mean, they pushed the subject in this direction, therefore I wanted to mention it, okay? Of course, my own and John Mador's work was more a fuzzy sphere. I will not go into these details. Fuzzy CP2, for instance, that was Alexander Strohmeyer, he's in the audience, and so on. CPNs and so on. So there are many, and there is, of course, Conlandi spheres and Botley spheres and blah, blah, blah. So there are many, many examples where you can realize all this, projective modules, it's already quite some elaborate work. As we know, I mean, Riffel jumped also to the fuzzy sphere case, so we had interactions with Mark Riffel and so on. It's beautiful. It's a beautiful subject. It was in the 90s. Now, as I said, first time 99 or so, the renormalization started, and really the question, can we apply this old artillery to this new subject? I mean, that's only the first question. And in addition, will it help? Will you just get the old BPHZ theorems, formal power expansion, or can you make really more sense out of it? Now, that's, so to say, the first subject. Phi to the fourth on theta deformed space, and a little bit I write Euclidean. What we mean is we start with a space R4, so we are on this level, space R4 theta. We have in mind operators maybe like this. Therefore, you remember I started the first lecture like this, of course on a domain and so on. Better go to while operators, so nobody can worry about boundedness. These are really bounded operators. E to the I, P, mu, x hat mu. And so the algebra is now very simple. UP, UQ equal UP plus Q, and there is this kind of extension coming here, P theta Q. I mean, indices contracted. And I'm sorry I didn't say in details. Theta is, of course, an antisymmetric matrix, theta mu nu. And in addition, we put rank theta equal 4. Of course, you can put it to 2. It was treated 2, so I don't go into such technicalities. It's better to have an inverse. So let's put it this way, which is, so to say, really more Euclidean invariant. Of course, if you put it, let's say, as we typically do, an antisymmetric matrix of this type, we break the SO4 symmetry, which would be behind. But it doesn't matter so much for me. At the end of the day tomorrow, we will remove a cutoff, and we will recover full Euclidean invariance. So that's on the way of regularization and so on. It's meant to be like a quantization of H bar. You see, then phase space becomes cells. And the idea would be, I don't know whether somebody really hoped for this, that everything will be finite. Like, for instance, you know, classically an electron should spiral into in an H atom and lose energy, and after a very short time it would collapse into the singularity. And quantum mechanics prohibits this. Quantum mechanics saves us, at least for certain years. But otherwise everything would collapse. Now, quantum mechanics smears because phase space has cells of order H, by the way, in phase space, H, not H bar, but anyway. So the hope would be, because singularities come because you put field operators at the same space-time point. Of course you shouldn't do, it's clear. But if you smear, you violate causality immediately, locality and so on. So it's a tragedy. We write phi to the fourth, of course, at the same space-time point. So we have to define what this means. Yeah? And the hope now we put cells on our space-time. In a way, yes. That plays the role of theta. Of course, you can say, these are 6 parameters, but no, there are 2 invariants. It's like an electric and a magnetic field, and there are 2 invariants, this one and this one. Okay. 2 constants. We can put it here and here, so I put 1 here if I don't put it to 1. So there's just to simplify. 1 constant, like H bar, there's a second constant, and it's a minimal length and a maximal energy, a minimal time, and so on, built in from the outside. Now we are here, differential calculus. Well, differential calculus is very simple, of course. Here, that's really very simple, much simpler than all this actually. D mu on the while operator, UP. Well, you think of differentiating, so it's IP mu UP. by definition, and it fulfills the ideas of differentiation, Leibniz rule, and so on. Now, I should say it is generated by an element out of the algebra, at least generated. One has to be a bit careful with multiplier algebra then, but well, let me denote it like this one. Where did I put the index? UP, where this x twiggle means just beta to the -1, so we take the inverse and assume it exists. And you see, if you differentiate, you would like to evaluate this bracket, you see this bracket makes, this bracket makes a theta, times the theta to the -1, that goes away and makes a p again, okay? Sorry? Sorry? Yes? No? No, no, no. No, no, no. Not yet. Oh, p mu are the parameters here. It's like in the commutative case chosen. Okay. No, no, no. But it comes now, actually. What is the trace? Well, the trace on this algebra of the generator is just the unity operator, which is delta in P. Now it's, I mean, that is, of course, here. Now, of course, the trace of UP times UQ at cyclicity is immediately from what you see, and I don't see so well. And, of course, Stokes holds, I mean, okay. So that is very, very simple and not, where are we? Well, fields, it's very simple here, but maybe I relax for a second. What is the definition of the field now? We start from a commutative field. So commutative in Euclidean, it's a stochastic variable. Now we Fourier transform it and we make Weil quantization. So it's very similar if I introduced the U's. I mean, it's a U operator here. That's Weil quantization. And I call it the field operator. Okay? So it's very simple. It's an L2 in the appropriate, so only space-time is quantized. I mean, that's commutative. I mean, these are stochastic variables. So in Minkowski, it's of course much more complicated, and therefore I'm not doing it. No, but people tried, as I told you. Then you start from a field operator, okay? You Fourier transform it, okay? Of course, then you have a tensor product of the Weil operator. That's what Sergio Doplicher, somebody knows the work, did, and Klaus and Dorothea and so on. So that's now of a product Hilbert space of the quantum mechanical Hilbert space, little h, and of the Fock space. Well, or the Fock space becomes a big Hilbert space in the not interacting case. Okay, here it's a free field, so to say. Now, that's of course much more tricky, and it's not clear. There's no Osterwalder Schrader in general, and so on. We tried to work a little bit on this, but okay. Just to say, here it's of course that would be of course Minkowski metric, yeah. While my scalars here are all Euclidean metrics. So okay, and they keep it now. Now, for later purpose, there's a small exercise, so to say. Let's put phi 1 up to n. Well, let's just write it to illustrate a little bit at least. Oops, I took such a phi, bj, they commute. And I have gotten e to the e pi 1 x hat, and so on, e to the I pi n x hat. Now you can do whatever you prefer. You have to reorder it a little bit, or better you use this Weil algebra. Where is it written? This one, okay? Several times. So what you end up is, of course, a product over L less than m of the phase factors, e to the I half, we wrote, PL beta PM. And that makes a big difference now compared to commutative quantum field theory. That's a starting point. Well, now we have, sorry, I write it explicitly, Pn of x hat, or use Becker Campbell Hausdorff, but it breaks anyway down, and so on. Now, so what is it? We take the trace. We take the trace here. We take the trace here. And this one is delta. Well, that's energy momentum conservation of all diagrams of everything which comes next. So energy momentum is beautifully conserved. But we have gotten these oscillating phase factors, okay? So we are now here, action. So the action we are discussing is a good old phi to the 4 action. It's a toy model, maybe for the Higgs, but anyway. Now, what did we say? We say a trace of a half, I guess the minus is welcomed here, and there are because somewhere there's an I and the I squares. So we have two derivatives, so we take the derivatives in the sense of the generators together with the field phi. That's like a gradient. I'm sometimes writing up and down in Euclidean, it doesn't matter by the way, but that's okay, that's our gradient. So everything is very simple. If I put a cutoff, which I will put, well, I can even put it here symbolically, which means these become all infinite dimensional matrices in this sense, because that's an infinite dimensional matrix in the appropriate Hilbert space. But we will cut it off soon. I mean, maybe here symbolically already. Now, plus m square half phi square plus lambda. Well, it's now only cyclic symmetry. Oops, therefore we don't put a factorial because of cyclicity. So the interaction is really phi times phi times phi. I mean, maybe I write it to. Therefore, I did this little exercise, okay? And the bracket is gone here. Okay, that's phi to the 4th. And the trace goes on everything. People, by the way, like to write it in terms of star products. Well, first of all, I don't like it so much. And second, well, it's on this level, so to say, identically. Of course, I don't know whether somebody would like to see the while operator smeared with a function f, while operator smeared with a function g is a while operator of f times g, and the f star g at a point x. Just to tell you, I looked it up, so to say again. What is good to remember? Some people write it in the like Kontsevich wrote it always exponential of, and then formal expansions. This we don't like. This we don't like. We would like to have strict, so to say, deformations, not formal deformations. And therefore, I like. If I write it like this one, zeta half, I guess. That. Oops, I'm sorry. No, then you make mistake because you don't like it. X plus z, yeah, right? E to the I y z. Okay, you can rewrite everything in terms of the star product, and you have an integration and so on. The main point is actually, here there's a square, and here is phi to the 4th. Now, if you have two operators with star, or in my language here with the operator language, you see immediately due to the delta function, if you have gotten only n equal 2, two momenta, the sum has to be equal, so they are negative to each other. And therefore, this phase vanishes. So here, no phase, no phase. Here there is a phase. So what is this phase? What is this expression here? Okay, lambda over 4. Maybe explicitly. Yes, maybe explicitly. I could write it once. Yeah, 1 up to 4. So we have the TPJs. Well, it's somewhere in, by the way, you see it. Here you have the phi free transforming by PG. And the essential thing is the product over the 4. And the essential thing is, of course, this product, L less than M, I half phi, PL theta PM. You would have, in local quantum field theory, that's more or less the same as this one. Now, if you would like to go ahead, it's very hard. What I mean is, for instance, you ask about renormalizability, which we did a couple of years ago, and especially because these phases occur, and typically you have to iterate and estimate and see that you find some bound of amplitudes and so on. So phases are for sure a bit complicated for this purpose, and therefore we went to a different base, and this base I will explain now. And so this is a theorem which well, it's too much to say. I will not prove it really. It's the following. This action, this model, let's say it's on 5 to the 4th on theta space, is not renormalizable. Therefore, I left the space here. It's not renormalizable. Of course, as I say, I'm not going into the big details, because the main problem is actually to cure it. And the first sign for it is what is called mixing. Now, the 3 people I mentioned last time realized also around the turn of the century that if you treat these models, and that's more or less generic, I mean, people saw it in very simpler models, actually, in 2-dimensional models, but these people around Seiberg, they realized a little bit more, and therefore they got the credit, and I think it's okay. Now, so we stay with this 5 to the 4th and do a one loop calculation, so to say, one loop calculation. That's fairly simple. So what are the Feynman rules? We've gotten a propagator, and this propagator, as I told you, the star disappears, so it's a good old one. If the momentum p flows in momentum space, it's really the propagator I gave you first time, this one. And now we have a vertex, but the vertex is different than what we did before. It's minus lambda as before, deltas of all the momenta flowing in, so up to 4, 1, 2, 3, 4. But we have to watch this kind of factor, and so on. So I write always the same, I'm sorry, PL beta PM. Okay. Now you see here we have to start somewhere and take one with the next, with the next. We have to put some cilium and say, we are going around this way. Encoding now a Feynman graph according to these rules is identical to go to ribbon graphs. Here you see, I mean, ribbon graphs means this one goes with the next, this one goes with the next, and so on. Yes, very good. That's it is. Tomorrow we do only metrics indices. Well, today even almost, except some hand wavings. Yes, I'm sorry, exactly. Yes, I'm sorry, I just wanted to say we have to put a cutoff, but here it's a bit early. We will put a cutoff right where regularized will be n, or it corresponds to what I called sometimes lambda, exactly. And I will say in a few minutes, a few times, yeah. Of course, yeah, thank you. Because otherwise I would rewrite this one. That's exactly the point. It comes in 10 minutes or so, exactly. Thank you. Okay, so yes, we have matrices, right, till the end. End of tomorrow. So I was hesitating because I wrote this. Of course, I will do it like this, but that's doesn't matter. I mean, I just draw my matrix ribbon graphs. So we come to ribbon graphs, as it's called, and ribbon graphs, and they live on a surface with a certain genus and with a number of boundary holes. So we are really on a Riemann surface, well, as everybody draws always, with a number of holes. And the holes are for what? we have to put external legs. Many people in matrix models too, they treat partition functions, also in strings and so on. Then you can always raise, which I sometimes do, but sometimes not, raise the hand and say, what about correlations? Which is much more tricky. You have to put a source, our term, J times magnetic field term, H times S yesterday and so on. And so here, so to say, you should think of a network of ribbons here. And then maybe you say, the 2-point function has 2 legs for one hole, because we start with even polynomials. 4-point function has such a contribution, but has also a contribution where all 4 legs are here and so on. Okay, we'll say a little bit about all this later on. So B is, so to say, 1 and so on. I mean 1 because 0 would be gravity, pure gravity. It's certainly interesting. And genus is, of course, 0 and so on. Okay, ribbon graphs. Now I'm not going into many details. The vertex is now this, except one loop calculation is what? It's fairly simple, except nobody realized, so to say, and I guess the weights are, no, the weight is 2/3 and 1/3 of contractions. Contribution to the 2-point function. Planar one is this one. Oops. And the non-planar one is this one. And that's, of course, new for compared to the old Feynman graphs. If you go to the ribbons, you see you have both. Now, what is it? The rules that is a propagator, let's say P runs here around, and it's trivial to see, I mean, due to the delta function, it's really only the integration. Yeah? So the phase disappears here. Now we cut it off, and it goes like lambda square, like in commutative theory. So there are infinitely many graphs which you could treat by BBHZ or so, which you could treat in principle, which are still divergent. So the hope everything is finite is for sure not true. But what about this one? That's a funny integral. So we get a contribution minus lambda third integral d for p over p square plus m square. And the phases don't disappear here due to this kind of, well, it's still planar, but it's irregular as we called it, so to say. E to the I p theta q that is left over from the phase, the oscillating factors. I mean, you put, you use energy momentum conservation, and such a phase stays, and Q is the outer momentum. Now, that's funny. It's finite. So that could make you happy. It shouldn't. Maybe in 98, 99, some people were happy. I don't remember at all. It's conditional convergent. You shouldn't take the modulus and you pick up the quadratic divergence. Now, and that people saw before these 3 people from string theory entered, if theta q goes to 0, it's a Euclidean momentum. If theta q squared goes to 0, it has to diverge, like a quadratic divergence, the constant here, which everybody can calculate. It's completely trivial. It's 50 times probably it was published somewhere. Because it's a bit a shock. It's an infrared singularity in a massive model. How can that be physically? Q is the external momentum. The external form momentum. So you see Q tiny. We never have had problems in local field theory when the mass goes to, when there's a mass. Of course, if I put a mass to 0, I have infrared singularities. That's an infrared singularity. Infrared singularity. So, of course, now, after so many years, I can say, oh, it's clear. Well, I don't know what. Physics sometimes goes like this. The mathematics tells you this. Now I can make an interpretation. And the interpretation is very simple. What's going on here? We have quantized, so to say, think of two variables, x1 and x2 only, or 4, that doesn't matter. x1, x2 became I theta. So it's really like quantum mechanics with 1 degree of freedom. And probably you have heard about what is called squeeze states. If you squeeze in one dimension, it will fluctuate in the phase space different dimension in momentum. Or here, if you squeeze a wave packet and localize in one of these coordinates, uncertainty tells me it has to fluctuate in the other coordinate very rapidly. So small distances in one direction are coupled to large distances in the other direction. And the outcome is this one. So now, okay, we can slowly understand, but that wouldn't be a big problem because one diagram, everybody can take the singular part, put it regular, I mean, put it to the action, additional operator, but these people were clever. Really fantastic, simple idea. They iterated this stuff. And now you can cook any theta to the 2p onto 3 singularity. Of course, now you can say, yeah, but you take one and make a chain. This I can handle, I sum up, yes. But these are not the only singularities. There are infinitely many singularities in the infrared. They go, as people analyzed, with the so-called HEP sectors. HEP sectors, and well, so infinite, because you can cook a complicated diagram. So to say, vaguely speaking, in this language, it appears if we have gotten here external parameters, and the sum of the external parameters takes the role of the Q, the momenta, the sum, total momenta of the external parameters. So if they go to globally to all together to 0, in or out momenta and so on. So that's a terrible story in a way, and almost killed the subject, except if we have Reimer in Vienna and time, and what we did is we filled this gap here. But of course, it was maybe 2 years or so work. We added one operator here. And realized when we add here a fourth operator, so phi to the is not renormalizable if omega is 0, and phi to the fourth is renormalizable. Okay. If omega is not 0. Okay. Now, it's really very hard work, and depending on the real time. No, that's the anticommutator. Yes, a very good point. Well, because how should I say, otherwise it takes too long time to go into more details. What did we do? Yeah, of course we didn't invent it from nothing. Therefore, I first did put the omega term to be 0. We went to the so-called metric space. Well, these are already matrices, of course, but to a little bit a different base. And that means we introduced really creation and annihilation operators over square root of 2 theta, and of course they're joined, and they make really the oscillator stuff which you have in first lecture in quantum mechanics or so, maybe second, okay? And then we have put a base of operators in our L2 space, where we put just, I'm sorry, in oscillators, you know you have a ground state, and then you have the first excited state, that's this one, we call it 1, and then we have the nth excited state, and that's given by a star to the power n over square root of n factorial on 0, we call it n. And this fn's we take is fnm in the Dirac bracket notation. drawn a little bit more rapidly than mathematicians. Okay, F and M. So these F and M's, it's just a base which is suitable for our purpose in our Hilbert space. It's delta F and Q, I guess, I got it. And the trace maps to 0, 0, like in muscles, base, and so on, and so forth. So the field now, how did we call it? The field like this one, is expanded in NMs, phi and M. These are now C numbers, F hat and M. And the action is now really a matrix. It's a matrix model where, I write it like this one maybe, of the many phis. It's a sum over n m's and p q's, and I've gotten a phi n m, a phi p q, and I put the quadratic parts to delta. I mean, that's now a tensor, of course. And then everything else is lambda over 4 factorial, and there is really a lot of phi summed over everything, so mp pq qn. So indeed, pq. It's a matrix model, and here, so to say, we don't have oscillations. That was the idea. Phases are gone, no oscillation, of course, signs, I mean contributions here, and so on. But this one is, of course, a bit a complicated object. Now, since we have broken SO4 to SO2 cross SO2, we can only rotate in these two corners anymore because of our choice. Then we have only one conservation loss. It means N plus P, maybe, is M plus Q, but okay. Times something, okay? And I don't write the something. It jumps in the indices because of the delta, or because of these brackets here, yeah? Because of the brackets. That's the point. Now, well, we analyzed it. And by chance, we learned about Maxner polynomials. And they diagonalize this. Well, actually, I can tell you also the following. You see, we have gotten 4 indices, but one relation, so 3 indices. So it's not really a matrix, it's a sequence of matrices with one parameter always fixed. Yeah? And you diagonalize the matrix and the sequence step by step using Maxner polynomials. But okay, it's only to impress you. We didn't know before of these Maxners. Anyway, it was possible to diagonalize and to handle it. And what we got is the delta. Yes, and of course I made a small mistake because all this is of course for an R2, but we have an R4, so we double everything, okay? Now we have gotten a lot of indices. So many. And the inverse is a propagator, and the inverse has a certain behavior in certain directions. That's just, so to say, to give a hint. When you put all these parameters equal and let m go to infinity, it goes like 1 over square root of m, which is a very weak decay, which means there could be phase transitions. And we associate this phase transition with non-renormalizability. So that's bad. So you have to improve it. What do you do? If you have a system which has a phase transition, you put it into a box. Then the propagator decays better. And the box is this term. That's like an x squared box. It breaks translation symmetry, but we will cover it tomorrow. But okay. And then we saw, that goes like omega square m square. A bit better, not very much actually. And here it went, I guess, like 1 over m first, but then it got 1 minus omega square, 1 plus omega square to the power m. It had an exponential decay. Omega is now between 0 and 1. Okay. Now, anyway, so that's only really epsilon starting point. And then it went on, and to save time, I just tell, because it's an old story, that we found there there's cancellations order by order, so to say. Otherwise, you wouldn't find it. How to say, to make a kind of joke, I can tell you the following. At that time, I applied, after we had finished this renormalization proof, I applied for money, and I got the referee report, which was the shortest of my life. 2 lines. The last time somebody found a renormalizable model was Toft, and he got the Nobel Prize, so give him the money. Of course. Oh, of course, we are very close in a certain, yes, very good point. But yes, I have to, how to say, to save the time. Completely right, we are extending in a certain sense the matrix models of Toft and also coming close to Kontsevich integrals, which are also matrix models, but particular ones. And we have a little bit a different one. That's exactly the point, yeah. Okay, renormalizability in the sense of formal power expansion still. I told you that's not enough, okay? That's not enough. Now, I think I skipped, so to say, a bit an explanation how we did really. We used the Bolshinsky equation, but that's maybe a bit too much. And now, I'm not sure, should I give a hint, so to say, what is renormalization? How comes that physicists like we are discuss always a running coupling constant? Who has ever heard of a running coupling constant? Physicists. No, and who has never heard about the running coupling constant? I have to, really? Oh, I have to hurry up and run. Really? I see. So the point is, well, we start always, maybe I erased the model. Where's the model? I erased it, but we start with certain parameters in that model. So maybe I should spend a few minutes at least on this. Also, it's a bit hard always in a few minutes. And the point is, we start with so-called Bayer quantities in an action. And then we would like to go to different scales. We are doing something which sounds a little bit what you saw in the lecture yesterday by Eric on scaling. We do always some scaling limits. And maybe I'll go to the second part and renormalization group flow, and I sketch at least a little bit of this type. Now, the first time we started with a free Euclidean field. And this one was what? It was the P, it was I Px, oh sorry, x minus y, over P square plus m square. Now we play a trivial trick, and I borrow this remark from Riverso because I like it to present it this way. There are many ways to present the ideas of Wilson, etc. But this one is, I guess it's easy to understand, hopefully, especially for mathematicians, I hope. Okay, now we can even calculate a bit different, e to the minus alpha, m squared, times I integrate, and I get, of course, heat kernel, which I wrote the other day. I mean, the first one, there's a 4, what is it, alpha, 4 by alpha to the square, because we are in 4 dimensions, okay? Completely trivial. Now, you know there's this stochastic variable here, and there are a number of scales. Now, if p goes to infinity, that's the complicated regions, that's the UV singularities which show up in our models. Yeah? That corresponds now, here you see it immediately, p going to infinity to the limit alpha going to 0. Therefore, it's better to slice this integral into a part which is 1 up to infinity, the same integrand, this one, bracket, plus a half to 1 d alpha, plus a half squared to a half, and so on. So a half for some number between 0 and 1, d alpha, and so on, plus, oops, 2j, 2j minus 1. So we split this stochastic variable, and it becomes 0 to infinity phi j at the various scales. And the correlations, I mean, we denote, so to say, this as the covariance of the field, which has frequencies in the appropriate range here, and call it C0, C1, C2, and so on, and Cj. Maybe j equal 1, so it's 1. Oh, is it 2? I don't know. 1. Okay, yeah. Okay, so I start with C0, C1. That doesn't matter. Okay, now we have split it now, so to say, the contributions, the frequency or momenta contributions to the various fields, and these phi j's should be distributed independently, just according to the frequencies which they have, okay? Now, the RG flow can be, so to say, explained in almost one line. Define frequencies, well, we make a kind of phi j, a field which has frequencies up to j. We chop it at j, okay? And now we take some action at the scale j, because I was asked also about such questions. Phi j plus all frequencies up to j minus 1, and integrate them over the slice to frequency j. And we define it as a new action. Hopefully it's positive, the results. Therefore, we take the logarithm and define a new action at scales of phi j minus 1. Of course, those who know will say, yes, it's a simple sketch of what Kadanoff, Wilson, and all these people got the Nobel Prize for. Not for this formula, but applying it to, I don't calculate critical exponents and so on. But the main idea, how to say, you can arrange it in 100 versions. What you mean is you integrate out certain frequencies and iterate now. Before at the beginning, in the first lecture, we spoke about renormalization, infinities of diagrams. There is no infinity now. We approach the singularity step by step, and step by step we jump from one action to the next one. Therefore, we have a dynamical system. We have associated a classical dynamical system. And that's, of course, a completely different idea, and completely, it's a new world, so to say. Of course, now in parameter space, in principle, if I write everything, I have to start here, and I write an ansatz with infinitely many parameters. So I am in a huge parameter space, hoping for that these dynamical systems have, for instance, one fixed point. And many of the operators which are connected to the parameters will die out by iteration. So to say, the coupling constant, you see the trick which is played in this formula, therefore it's empty. There is an action with an index j, and there's another one here with j minus 1. You can immediately say, are there fixed points in our case? Well, That's a challenge to find. That's, of course, a tricky question. You can here start with phi to the 4th, and here you will get phi to the 6th terms, and so on. I mean, you cannot really solve it from nothing, so to say. It's a highly nonlinear complicated system. There are some models where you can really solve this equation as a fixed point equation, but typically also Wilson did. I mean, you expand then this kind of thing and get, so to say, you start with an action, for instance, our lambda phi to the 4th here, and here you have a kind of g to the minus lambda at the scale g minus 1. That's a running coupling constant now. Here we start with lambda j in this action, and here we end up with lambda j to the minus 1, and then we try to iterate. Yeah? And what do you get here, for instance, in the simplest case? Of course, the first contribution is this one. What will be the next one? The next one contribution comes from such a bubble, and what it leads to is in any way a positive contribution times something which goes like lambda square, and of course next terms, I mean, unfortunately, in a way. Now, this iteration, for instance, can easily be solved if you go to like this kind of, well, it's of course hand waving in a way, but minus beta lambda j to the minus 1. To that order, I replaced it by this one already, yeah, just to simplify. Now I divide by both and get this solution, this iteration, which has a solution which is lambda j equal, well, that's an equality, lambda 0 over 1 minus lambda 0 beta j. It's very simple. Now, beta is positive, I said, in this phi to the 4th model. It develops a singularity at finite cutoff, so to say. That's a lambda pole. That's a lambda pole. The lambda as a function of j starts somewhere and develops a singularity. So that almost killed local field theory. Now, as I said before, I mean, the picture is the following. You have to identify, so to say, how many dimensions, how many operators and quantities and parameters are attracted by the fixed point, and how many are repulsed. And so the question is, well, if a quantity goes to 0 anyway as a function of the cutoff, then you get rid of it. For instance, nobody asked me why I'm writing all this phi to the 4th. I could write phi to the 6th, phi to the 8th. I mean, who cares? But of course, these are all so-called irrelevant operators. These are the irrelevant operators which under such a mapping would die out. Phi to the 4th is not irrelevant because the coupling has no dimension. You know, the counting is the following: d phi x, d phi squared, that determines the dimension of the field. In 4 dimensions, you get rid of 2 due to the Laplacian, and therefore phi has dimension length 1 over length. That's 1 over length to the 4th, so lambda doesn't have a dimension. If I make the same in gravity, gravity has a dimension, and that's bad. The gravity constant has dimension length squared, and therefore it's non-renormalizable. So to say, that's the ultimate simple idea behind. And okay, so is that more or less understandable? Now the point is, we did an analysis which is very similar to this one in our case, and in the case of this complicated model, and wanted to identify the so-called relevant operators, relevant or marginal ones. Well, relevant ones, you have an increase of such a, if you make such iteration, you have an increase of the quantity, and these you have to fix through a renormalization condition, and that makes the stuff quite complicated, but we have to identify how many operators are really relevant and how many are irrelevant. And in our case, we realized that there are, so to say, I can write it here under the Meixner. Oh no, the theorem is gone. The point is, what we deduced is there exist 4 relevant marginal operators. Now, and of course, 3 were the starting points. With 3 we started with. I'm sorry I erased it, but the 3 you know. And the 4th one, well, you can choose various operators. We have chosen this kind of x squared, phi squared term. And that has special properties, that's the point. I mean, without knowing, we have chosen it first. Especially, we tried to do then a one-loop calculation. So what I sketched before, so to say, this loop calculation and also for the 2-point function. And you realize what happens to the coupling constant. Because you see, it's a kind of model which is almost as your old one, but deformed. I mean, to the ribbons. We went to the ribbons. It's a bit different. I will, the last lecture deals only with the matrix, with the behavior of this kind of matrix model. But nevertheless, of course, for the lambda is a function of the cutoff, which, well, I can denote it as J, but it corresponds to lambda, big lambda, I mean the UV cutoff. Starts, of course, as if it would develop the singularity from before, but then it's bending off and has gotten a limit. And why is it like this? Well, we have gotten a second operator, omega. Unfortunately, I erased the operator, but you remember the good old lambda phi to the 4th and the new operator with this omega term. And they both form now a dynamical system and influence each other. And the point is, well, they depend on the scale. And you take the logarithmic derivative with respect to the, with respect to the cutoff, and do a one-loop calculation. And what you end up is, except for constants, which are more or less related, almost the same, you get a term which goes like the square. I mean, that would be the parabola. That would give the singularity. And a second behavior, second differential equation for the omega parameter. And you see they influence each other. The omega parameter flows to, and it squeezed to 0 up to 1. And if the omega parameter flows to 1, this flow is finished, and this flow is finished too. So both are finished. I've never seen such a behavior in any model, in any statistical or quantum field theory model, and therefore they are stuck. In terms of the so-called beta function, which is, people call this derivative the beta function for the coupling constant, the beta function is 0 up to 1 loop. That's what we did. But we did something more. We influenced the Barry's group. Also, you belongs for me to the Barry's group, Axel, fortunately. Yeah? And they jumped to the subject around Riversaw, Jacques Magnon and Isadore and who else? Gura. Yeah. And you jumped to it too soon. So, and they realized heavy calculation to 3 loops, the beta function vanishes. And then they produced a beautiful paper proving to all loops the beta function is 0. Of course, in perturbation theory for the lambda parameter. And omega flows to 1. So next time we will put omega equal 1. And then the matrix model simplifies. Unfortunately, it disappeared, but I could start with it this next time. So we will just go to this fixed point which we discovered, and it's a matrix model which is complicated enough for the last hour tomorrow, and for us too, and for me especially. But you see, it simplifies a lot, but nevertheless, it seems to be non-trivial and almost have all the properties of a Euclidean quantum field theory in a particular limit, which we do in addition. But the main point to learn is that it has gotten beta identical 0 non-perturbatively, what we discovered in the model. And so next time I tell you how to go to correlation functions for this matrix model, actually. Thank you very much.